All right, once again, welcome to our webinar where we're going to showcase how you can learn to build your own reliable workflows for detecting millimeter ground movement using our newest release, PSI, or Persistent Scatterers Interferometry workflow. So welcome, sit back, and enjoy your time. If you wish to engage with our team at any point throughout the webinar, please feel free to do so. You can do this by accessing the questions panel, which is located on your GoToWebinar control panel. And then you can type your question into this control panel here. At any point, if there's a question based on something we present or anything you're curious about related to our technology or anything around our offerings, we would love to hear from you. And you don't need to wait until the Q&A period at the end. We will open up questions towards the end of the webinar so that we can address your questions directly here. And we always do our best to get to everyone's questions. And if we don't get to your question, of course, we will provide it in a written text afterwards. I'd like to take this moment to just introduce our presenters. So starting off in our lineup, we have Gabriel Gosselin, who is our INSAR senior scientist and our lead for INSAR technology development. So welcome, Gabriel. We also have Jason Flatt, our solutions engineer. He is one of our regulars here on these webinars. So once again, welcome, Jason.
It's great to be here, and hello, everyone. Looking forward to presenting some interesting results later on in the webinar.
Wonderful. And then myself, I'm your host. I'm a product marketing manager here at Catalyst. And once again, I'm really excited that we're here to showcase to you this latest technology. So we're going to go through a very quick overview of what we're going to be showcasing in this webinar. So we're going to start off with just a very brief introduction about Catalyst and about our offerings. Then we're going to go into a little bit of an overview of our INSAR workflows. At this point, we'll introduce our new Persistent Scatterers Interferometry workflow. Then we're going to explore some results with Jason. And then Gabriel is going to take over and walk us through the science and the workflow for our new PSI workflow. And then we'll finish off at the end with a questions and answers period where you can ask our team anything. And once again, if any questions come up, feel free to type it into the questions panel before we get to that point. And we will do our best to answer your questions live. And if we can't answer it live, we will certainly respond to your questions or post your questions up on our website. So Catalyst is a new brand that was launched back in October. So it's a PCI Geomatics brand. And our main goal by launching this brand is to really simplify Earth data. And this is to bring Earth data or data that's derived from Earth observation and other Earth measurement apparatuses to more people, to more end users. So this is both geospatial professionals as well as end users. And we're trying to make sure that the technology and the information can be more readily available and accessible in order to help make our planet a better place for tomorrow. Our different product lines include Catalyst Professional, which is formerly Geomatica, Catalyst Enterprise, which is formerly GXL, and then we have three new products. We have Catalyst Microservices, which is our cloud-based solution, our processing data on the cloud. And then we have Catalyst OEM and Catalyst Insights, which is our information or web-based information product, where you can easily access information derived from Earth data. Today, we're going to be focusing on a technology that's embedded right now into our Catalyst Professional solution. So this is Catalyst Professional, formerly Geomatica, is our leading geospatial desktop suite that's really designed for photogrammetry, remote sensing, and Earth observation science applications. So we can access it through subscriptions or perpetual licenses. Our main areas of emphasis or focus with Catalyst Professional is photogrammetry and mosaicing, interferometric SAR or INSAR, synthetic aperture radar processing, so other aspects such as pulsar or copol, so compact polarimetry, and a variety of other applications, object-based change detection, CCD, so there's a lot of other applications we have here related to SAR. And then, of course, image analytics around object-based image analysis and feature extraction and a variety of other image processing capabilities that you can build into your workflow. Once again, the real focus for today is our INSAR capabilities. So we have two main workflows for looking at or analyzing ground deformation using INSAR technology. And this is our differential INSAR, or D-INSAR, as it's often referred to, which you can see over on your left. And then above at the top, you can see our newest addition to our capability sets within the INSAR family is our Persistent Scatterers Interferometry, often known as PSI. So we'll describe a little bit of the two in just a moment. In terms of differential INSAR or D-INSAR, so this is really the ability to create a field where every single pixel is essentially, we calculate the deformation for each pixel over between two SAR pairs. So the inputs are really INSAR pairs, which can often be multiple pairs. As an output, we get this, once again, this field representation, as you can see here, where every single pixel is provided with a deformation value, which can be good and can be bad in certain cases. And the common applications for this are things like geohazards, looking at general high-level trends over an area. We've seen it often used for tip and cue, which is the concept of identifying where at a larger level or a larger scale where you might have deformation occurring, and then using higher res imagery as well as say the PSI workflow in order to zoom in and get a more detailed and accurate representation of the area. There's other aspects like glacier tracking, permafrost. There's a lot of applications for differential INSAR. And one of the big caveats or aspects to just keep in mind when it comes to differential INSAR is really that we're extracting these values for all of the different areas. So where you have high coherence between the two images, we can still get very, very accurate results. The problem, the difference is, or the main difference between this and the next one we're going to showcase, is that by not using a full stack of images, we don't necessarily know which ones are the stable points and which ones are not. So it can be a little bit more difficult to be able to identify specifically which pixels are more, you can have higher confidence in the measurements versus others. So that's where we are going to introduce our newest technique, persistent scatterers interferometry. So, but once again, I just want to highlight within this for the D-INSAR that there is a lot of very valuable applications for this, and it really just depends on what you're trying to do. So here's actually a recent case study that was done and actually presented yesterday at GeoConnect, and this was done by Up42. And basically, they used our latest our processing block on the Up42 marketplace in order to compare or look for deformation in the days or weeks leading up to the devastating landslide in the Rishi-Ganga Valley. And what they were able to identify was that there was clear indicators of significant deformation or movement of the ground in this area in the weeks leading up to the actual landslide itself. So this is an incredibly important application because it can really help us provide early warning signs, and this can ultimately lead to saving lives and reducing the damage or mitigating the damage on the surrounding areas. So quick plug here, check out our newest, the Catalyst Ground Displacement microservice, or on their terms is called the processing block on Up42. If you sign up now, you'll be able to get 10,000 free credits. Some conditions may apply, but go to up42.com and check out our latest capabilities and check out their marketplace. Okay, so this leads us now to our newest, so what we're introducing here today, which is our Persistent Scatterers Interferometry. So this is a different type of technique that leverages INSAR, but also leverages a stack of imagery. So in this case, we want at least 15, some papers will say even up to 20 images or SAR images in the stack in order to compute best results. And then the output from this are individual points, where the points are reliable measurements of that are capable of detecting up to millimeter movement. And the applications for this are really focusing on infrastructure monitoring, because it's great for especially linear infrastructure where we have very small linear features that need very high resolution imagery. So one of the benefits of PSI is you don't need to do pre-filtering or use multi-look imagery in order to analyze the results accurately or use or be able to calculate these measurements, which means you can use the highest resolution imagery possible. The other big benefit about this for certain, say, monitoring applications, particularly around civil engineering and infrastructure, is that the points that we're left with are what was known as stable points. So this means that we have a higher confidence or a very high confidence that these points and the measurements in these points are trustworthy. So it's a it's a really good application for ongoing monitoring sorry, workflow for ongoing monitoring applications. As if you drill into the individual points, so you're not just getting a single measurement with each individual point, you're actually getting a variety or a stack of measurements. So each point will represent multiple measurements throughout time. So then this can be used for further modeling and analysis. So you can start to see what's the velocity of the ground movement. Are we seeing moments of acceleration in the ground movement as opposed to just getting one single individual measurement or point through time? So we get this from analyzing and processing that stack of imagery. And then one of the benefits with the techniques we're using is that each point includes measurements at equal intervals. And this just helps support modeling techniques and also ensures that we don't have any crossover in terms of the time measurements of the deformation. So at this point, I'm going to hand things over to Jason, who is going to take us on and help us explore some of the initial results before we go into the workflow and discuss some of the science.
Wonderful, thanks, Sean, and hello, everyone. So as Sean mentioned, I just want to showcase just a quick demonstration of a use case with the PSI workflow, monitoring deformation across the city of Vancouver, Canada, which is a heavily urbanized area. What we did is we processed RadarSat-2 imagery, which around 2-meter resolution. We had 16 pairs or 17 images with between the dates of August 8th, 2013 to February 25th, 2015. And so we processed the stack of data with the PSI process, and I'm just going to showcase the results in a moment. Just going to change presenter and show my screen. Wonderful. Alrighty, so what we have here is just one example of the ingested images processed underneath a Landsat image. So first, working with an SBAS approach, we employed that to identify the interferometric pairs based upon the perpendicular and the temporal baseline. Following that approach, the images were then ingested and co-registered between the pairs. And these co-registered pairs, we were able to then extract or identify the persistent scatterers based upon an amplitude dispersion method. And what we see here is the results as expected, where the points that are collected are behaving consistently across the multiple data sets, so they're not changing. So what we see, for instance, in areas of vegetation with the trees, since there's a lot of movement between trees at different dates, could be the leaves with the wind, persistent scatterers aren't collected there, or even over the water and the boats, for instance. These are there now, but in other images they're not. However, we do see a high density of points in those urban areas. So this is why it's advantageous to utilize the PSI workflow for urban or barren regions, which is again useful for infrastructure monitoring, for instance. So once we generated the persistent scatterer candidates, we then performed we extracted the interferograms, performed the flat Earth and topographic phase correction, orbital correction, phase filtering, and we corrected for the topography because we wanted to extract the deformation. And then we unwrapped the interferogram along that PSI network and calibrated the stack, or calibrated them and stacked them, and then represented them based upon a color coding here, which we see trends, just to visualize trends. And what we're seeing right now is blue regions are representative of more subsidence, while the redder regions are areas of more uplift. And there, of course, are other colors for stability. So each point has a variety of measurements built into it over the time period, so we can actually analyze it and visualize temporally how the points or the area is changing. And so just in an overview, for instance, we can see that on the west side of the area, there's more subsidence around where the delta is, while further into the city, there's some areas of uplift or just stability. But what I want to do is just zoom in, for instance, to the airport. So I'm just going to, where there is areas of subsidence. So just give me one moment. So we can see we have a few options, quite a number of points being collected here. I'm just going to zoom in, for instance, to the runway. I'm then going to select on one of the persistent scatterers we collected here, and I'm just going to select on the stack that we generated that contains all the cumulative deformation products so that we can analyze it through time. I'm going to select the INSAR temporal chart, and we can see over the year, over the period, how the area is changing in millimeters. So it's going down, but then there is a spike, but then it goes back down in subsidence. So this is the cumulative displacement. And of course, we can look at other points. We can extract this information as well for additional analysis. So this is just one example of employing the PSI workflow in an urbanized area for cumulative displacement analysis. Back to you, Sean.
Wonderful, thank you so much. All right, so that is just a quick overview of some of the results that we've generated with the Persistent Scatterers Interferometry workflow that we've now released, and basically over the Vancouver area using RadarSat-2 imagery. And of course, our sensor or our algorithms and workflows are sensor agnostic, so we can work with majority of the both commercial and open data sources available on the market today that are capable of doing INSAR. Quick validation note. So we have a study that we performed. Actually, it was a little while ago over Cold Lake, Alberta, which we did with MDA using RadarSat-2 imagery, and just to showcase the type of accuracy that can be achieved when you know that you are collecting over stable points, such as these corner reflectors that were installed on this pipeline. And as you can see, we have a very high correlation, a very high accuracy as compared to the ground truth that was collected using ground surveying equipment. So we're continuing to do more surveys. More studies. We have a couple studies which we've recently done with some clients, which we're working with them to get permissions to be able to publish. And then we're also just finalizing a few studies, which Gabriel can go into a little bit more depth about regarding the accuracy using a variety of different sensors. So those look forward to more studies being published shortly on our accuracy and validation against ground truth. So at this point, I'd like to just open things up and engage with everyone here to understand a little bit about what your interest in INSAR is. So why are you interested to build your own INSAR workflows? So in this case, you can select all that apply. So 2 seconds while I launch the poll. Okay, so as you can see, we have a couple different options here. So perhaps you're just interested in performing research, whether you're government or academic. So if you're just looking to understand this and include this in studies. Perhaps it's more for education purposes. You wish to use it within your own organization. You're offering consulting services and you wish to build this into your your portfolio in terms of your different service offerings, or perhaps you're more on the developer side and you're looking to build this into a web service or integrate this into some other offerings you already have on your web service. It's very interesting. So right now we're getting a lot of various answers. So it seems like the vast majority are research, but we have still a significant number of people that are interested in building this into their own consulting services, as well as using it within their own organization. And then there are a few that are looking to build this into a web service. So we really appreciate your insights along this. It helps us understand where we should build and making sure that our technology is relevant. So I'll keep this poll open for just another, let's say 10 seconds. So if you haven't got your vote in, or you haven't got your response in, please do so now, because we're going to be closing the vote or closing the poll in about 3, 2, 1. All right, well, thank you so much. Let's just share those results here. So we can see that there is a vast majority, about 60% are interested in research, followed by 27% education, and then 24% for use within your own organization, 22% so that you can offer or add this to your consulting services, and then 9% wish to build this into a web service. So once again, we really appreciate your participation in these surveys, and it really does help us understand what technologies we should be investing in and capabilities that we can then offer. Okay, so just gonna, before we go into the bit more of the science and an overview of the workflow, I just want to quickly provide a high-level overview of the value of this our new approach, which Gabriel is going to go into more in detail about. So one general value is our sensor, the fact that we are sensor agnostic, and the ease of use of using our technology with a variety of different data sources. So compared to a lot of other packages out there where you have to understand both the INSAR workflow as well as how to use particular data sources. Just for example, where do I capture the metadata? How do I do certain calculations in order to provide the right inputs? We do all that for you. So all of that is provided by our solution. So the way that our workflow works with, say, Sentinel data versus TerraSAR-X data versus RadarSat data is all the same. So you only need to learn the actual workflow itself. We treat all of the different sensors, once you bring it into our software, they are all sort of normalized to a common format so that they can easily be used in the same way within this workflow. The other benefit about the approach that Gabriel is going to describe in a moment is that by using this method, or using the method, which is we actually use a hybrid approach, is that we're able to capture a higher density of reliable measurements that are capable of detecting millimeter ground movement by using a hybrid approach, which I don't want to give too much away, but Gabriel will talk about it in a moment. And then the other big benefit is our processing speed. So this has just been something that we've constantly put emphasis on, and something that we know that our customers and partners really value, is the ability to generate the results in an expedited time frame. And we do this by leveraging a variety of architectures that really make the most out of the hardware that you are implementing. And Gabriel can also provide just a quick example about the performance that you can expect with this workflow and our new algorithms here. So before I hand things over to Gabriel, I just want to really, for those of you who are not INSAR experts or specialize in interferometry, just a quick overview about what these two concepts are. So we have INSAR, or SAR interferometry, which is really the science and the technology that's used to detect millimeter ground movement. And it does this by analyzing the phase response from a pair of SAR images and looking at the difference. So we end up getting a line of sight displacement between for the ground between for a particular area between two images. So this is what's able of being sensitive enough to detect up to millimeter level changes or ground movement. And then by leveraging our persistent scatterers interferometry, really it's a technique that leverages the full stack of SAR images that you have in order to identify where are the stable points and throw away the points that we don't have confidence in, so that in the end you're provided with a layer where the points that you do have, or you're provided with a network of points of reliable measurements. So it's by combining these, leveraging these technologies and techniques that we're able to provide the output that Jason showcased to you earlier. Anyways, with that, I'm going to hand things over to our scientist, our senior INSAR scientist, Gabriel Gosselin. Gabriel.
Okay, thank you, Sean. So just to resume a little bit before we go into the workflows, so the INSAR basics, so how can we measure millimeter deformation over the surface, is based on repeat pass interferometry. So we have satellite that follow some orbits, and since we know using the state vectors exactly the position of the satellites, and also we know at how fast the wave is moving at the speed of light, so with the two radar we can get an exact measurements of the distance between the satellite and the surface. So if we remove the effect of the topography, we can extract only the portion of the signal from the line of sights, because all the measurements are from the perspective of the radar for the moment. And based on that, when we compare between repeat pass interferometry, the number of oscillation number of waves between the two satellites, and with the time measurements, we know exactly within the cycle of the wavelength how much displacement there was between the two signals. So this is basically how we can retrieve this millimeter measurements if it doesn't exceed like one cycle, one wavelength. So next slide, please. So there is a lot of different techniques if you follow like scientific papers, and there is a lot of concept and lots of hybrid technique. So there is two big concepts behind our workflow that we're using. So we had before like the differential interferometry, what I call the 2D unwrapping using snafu. Now what we can do is using the small baseline interferometry to ensure that all the perpendicular baseline within a stack of data are within a certain range, which for deformation usually, if I'm really stringent, I will use a perpendicular baseline within 100 meters, so between -100 to 100. If I have less data to work with, I can go to 200 meters with a perpendicular baseline. But the SBAS approach also allows to use more time intervals. So instead of doing a purely sequential acquisition scheme, so I will compare my image A to B, B to C, C to D, I can use multiple combination. And why we're doing that is to increase the number of observations. So if there is a bad interferogram, which can always happen due to, let's say, weather conditions, you won't create a gap in the time series, a big gap. And also by having more measurements, you increase like the statistical like reliability of your velocity estimation at the end of the process will come right after. So in some persistent scatterers interferometry application, they will usually accept maybe one reference, so one single reference file from which you compare all the dependent file, or some other application will use like sequential pairs. Here, what we're doing in the case is we allow for all combinations, so we can combine the richness of observation of the SBAS approach and to be more stringent on what goes into a stack with the Persistent Scatterers workflow, as Sean said, that can extract lots of reliable points. So we're working only with points on which we have confidence, and all the low coherence area of kind of wiped out from the process. Next slide. So this is what I was saying. So the baseline is really one important concept if you want to do a good application. So if you're doing deformation analysis, you have to stay within 100 meters or 200 meters. You can go a little bit higher if you have longer wavelength, but usually you try to have very like a small perpendicular baseline. And of course, you can always increase the temporal baseline. So instead of looking at only like every subsequent pair, 1 versus 2, 2 versus 3, 3 versus 4, you will then use multiple combination, like 1 versus 2, 1 versus 3, 1 versus 4, and 2 versus 3, 2 versus 4, and so on. So that's the concept between this hybrid between PSI and SBAS. So next slide. So what we're looking, because there is different way to define what is a permanent scatterers. Is it based on the coherence? Is it based on the measurement? Is it like a sophisticated measurements? One of the most current approach and one of the most general approach is to use the amplitude stability. So you have a stack of co-register image and you're looking for the points that have a low standard deviation across your stack. So they can be either like points on bright buildings or points on flat areas. Is really the stability. So you can have like really bright points, but if they are not consistent through the stack, they won't be considered as a permanent scatterers. So on the right, this is the concept you have. So you dig through your stack and you find the points that do not vary below a threshold. We call it the amplitude dispersion threshold. So usually what you try to have is around 2 to 3% of your image as persistent scatterers. And if a point is not consistent across all the image in your stack, you remove it. Next slide. And one of the other like things we do, which is a little bit different, is when you have a dense series of observation using like a small baseline interferometry approach, is usually you compute the interferometric midpoint. So you have your equation, you have your dependent file, you have your reference file, you compute the velocity between the two, and then you will assign this velocity to the midpoint, the point that we see in green. But when you have multiple pairs, when you are that are overlapping, it might happen sometimes that the temporal midpoint, you could have like dense observation over certain area, and you can have like a low density over the other area. And sometimes if you have multiple points that are close in time, you can have like spikes in the velocities, as we see on the left. So the approach that we are using the decomposition of the velocity is we're doing like lots of matrix inversion and lots of matrix calculation to get smoother velocities estimation. So once we have all the temporal midpoint, we decompose the whole time series into equal overlap. And after that, by some mathematical process, that allows to get like smoother velocity measurements. And this is based really on statistical approach. So this is one of the basic principle for PSI workflow. And the next slide. And for the more scientific view, because we offer like different level, this workflow is embedded in different product. Goes from the end-to-end process in which you simply have to enter like your input folder and we get a result at the end. But as all algorithm, they are embedded in what we call module, and here between parentheses, this is a different algorithm. So the PSI workflow is something that is really modular. As we have mentioned, there is this workflow that you need to complete the full PSI processing is sensor agnostic. So it won't differ if you have TerraSAR-X data or Cosmos CAMED, or if you have Sentinel-1 or RadarSat-2. It won't differ. If a sensor is supported, this is the workflow that you have, or one of the variation. So in input, we accept different input mode, like small baseline interferometry. You can use, if you want, sequential, or if you can use a single reference. So you will have usually one reference in the middle of your stack and you compare other dependent to that file. And one of the first other things that you have to do is once you ingest your data, you can use an area of interest that will be reprojected onto the slant range geometry of your image. then goes to the co-registration. And here, this is like a pretty common operation that we're used to do for differential insert. You do your co-registration and then branch out. This is where you track your phases, like the run interferogram, the topographic interferogram. You can adjust for the orbital adjustment. So if there is orbital drift between on your baseline, you can correct for those systematic effects. And then you filter your phase if you need to, like using the Goldstein filters. So that doesn't filter the intensity, but only the phase. And then with your co-register pairs, you will extract your persistent scatterers. So you do your stack, you analyze it, and you extract everything that is stable. And once you have your persistent scatterers map, now the two workflow come back together, and we are really at the heart of the persistent scatterers approach. So the next step is really to do the phase unwrapping for between the persistent scatterers. So what you have to do at that stage, and it's done by the algorithm, of course, but it will connect the points using a Delaunay triangulation, and then it will unwrap the phase along this network to balance out the residuals. So just as a rule, just to give you an example, I've processed a stack of TerraSRX data. I had 30 image, but for 14 millions of points, it took 10 minutes per interferogram to unwrap. So this is a really fast process. If you compare it to snafu, that could easily take like maybe an hour, 2 hours, depending on the amount of multi-looking you have done. So once you have your network of unwrapped points, you go to the calibration, and here there is different technique. If you don't have any calibration point over your area of interest, you can always let the software decide. So what you will do is you will look at the center of the image. You will take the point with the less amplitude dispersion, and it will use it as an anchor point, mostly to remove all the offsets due to the unwrapping. So with every unwrapped network, you have an offset that is inherent to the phase unwrapping, and they will anchor those together using this point. But if you have calibration point, like you have surveying points, or if you have points that you know they're not moving, you're allowed at this stage to enter your own points of calibration. After that, really where how the mathematics comes together is you solve for the displacement velocities. So you have your stack of calibrated deformation. Now it's time to estimate the velocities, usually in millimeters per year. And then after that, you apply a model. So you have your time interval, and then you will compute the velocities for those time intervals. And you do some statistical fitting to have a smoother velocities. And then once you have your velocities, you can go to the last pieces is to compute the displacement. And you have the choice in between computing like the cumulative displacement, or you can have just the displacement for every layers. And what you get in output is a stack of data that you can convert to points and carry your analysis. And now this is where like the mathematics stops and where your science starts. It's where you study your problematic at this stage. So is there a next slide for me, Sean?
No, that's
Okay.
great, Gabriel. Thank you so much. Yeah, so one of the things I want to just make sure that everyone takes away from this slide, and that Gabriel mentioned it earlier, is that for the more research-oriented and academic audience members, we expose these algorithms and we break them down into these individual modules where we give you the option to sort of turn every knob and adjust every parameter and really use it for those kinds of applications. But as Gabriel also mentioned, this can also be run in a much more automated, complete fashion. Sort of, you point to the stack of imagery you want to process, set up some very basic input parameters, and in the end, you're provided with your displacement layers. So we're very flexible when it comes to how you can leverage this workflow. So this brings us to our final survey question before we go into our Q&A session and just sort of round things out here in this webinar. So as I queue this up, just curious to know what SAR or INSAR processing packages are you using today? And feel free to mention multiple if you're leveraging multiple packages. So we have a couple packages here right now. We have Catalyst Professional, and we've just introduced our new INSAR. We have the NV SARscape, Gamma, Snap, and other, which also can be none. So if you're using a different package that's not listed here, I'd love in the comments section or in the question section if you're able to just sort of identify what packages you're using today. And we'll give this another few more minutes, or sorry, a few more seconds, because we already have a majority of people have voted. We can go through. And right now we have, it seems like the majority of people are sort of split between Snap, Gamma, and Catalyst Professional. So these seem to be the leading ones, at least within this audience, and it makes sense that it is our audience. So we'll give you just another, let's say 10 seconds to get your vote in, to get your response in, and then we'll close the polls here. Okay, wonderful. So I'm going to close the polls in 3, 2, 1. All right, thank you so much for your response. In the end, we had Snap had a slight lead, followed by Catalyst Professional, then Gamma, and then other and NV SARscape. So thank you very much for participating there. So just to round things out before we go to our Q&A session. So if you wish to learn more or you wish to give this workflow a try for yourself, so you can always reach out to us and request a demonstration or set up a meeting and we can help showcase to you. We also are putting up some tutorials online, so those will be up very shortly. And of course, you can download a free trial of Catalyst Professional, or you can access and purchase or subscribe to Catalyst Professional for a very low monthly or annual cost. We also have an upcoming webinar where we're going to be showcasing our latest processing block or microservice that's available now on Up42. Same thing, it does leverage our INSAR technologies, but it's showing how you can use it in a more cloud environment. So it's ideal for especially building your own web-based solutions or building it into you or integrating it into your workflows. And what's also great about it, it's a very simple setup. So this one's just really more calling the API, setting up some basic parameters, choosing your scenes, and then running the output. So join us on April 8th at 4 p.m. Central European Standard Time or 10 a.m. Eastern Daylight Time. So, and you can go to this link. So go to our webinars and register there. We'll send out as well a follow-up where you can access the link to this registration. Okay, so with that, we're going to close out this webinar with a question and answer. So I'm going to ask our panelists, with Gabriel and Jason, to come back online. And we really appreciate, there's been a lot of questions that have come in. So I don't think we're going to be able to get through all of them, but we'll do our best to get through as many as we can. And once again, if we don't answer your question here live, we do post all of our answers to the questions that are asked on the website with the recording. So you can always come back and access it then.
I can go through a couple of questions if you want.
Sure. You know what? Yeah, if there's a couple questions you wish to answer, by all means.
The first one is compared with other software, how fast it runs, mainly in the unwrapping part. I don't have direct time estimation with other software, but as I've mentioned, I think 10 minutes ago, to unwrap 14 million points, like it's a complete TerraSAR-X image. So this is approximately like 20% of all the pixel of a TerraSAR-X scenes. It took 10 minutes for 14 million points. So that will be 10 minutes time the number of pairs you have in your stack. So that's pretty fast.
Just to clarify, you're not using anything, you're not using like a processing rack or anything, you're just using your desktop computer, or?
Yeah, in that case, it's completely like just a sequential processing on my desktop computer. Because
Wonderful.
the unwrapping, you could use it like in parallel. You can unwrap multiple like scenes at the same time, but it will be 10 minutes per interferogram. And this PSI workflow is not using snafu. This is related to another question. Do we need to download snafu? For the PSI workflow, no. The unwrapping is done over a network of points, and snafu is not used. This is another like technique, and this technique is 2D. Another question was related to the unwrapping. Is it a 2D or a 3D unwrapping? So every layer of the stack is unwrapped independently. So we are not looking across the stack to do a 3D unwrapping across all layers at the same time. This is 2D unwrapping. Another question is, all the SAR image must be of the same type, same polarization, same ascending, descending order, same band? Yes. For INSAR, it's absolutely necessary that you have the same ascending or descending. You can process two stacks separately and combine the results at the end, but it's necessary to have all ascending or all descending. It's necessary to have the same viewing geometry. So if you're working with ultra fine data for representative, for instance, you cannot mix it with fine data. And also, if you working with the HH polarization, you have to carry on with the HH across all the stack. You cannot switch to the vertical one. In theory, if you're just switching the polarization, could not like give, is that just the face center like in dense area or in urban environment won't be at the same place, so you could interpret face centers at different places due to different penetration depth related to the polarization. So this is really not recommended, and the software will just detect that if there is different polarization, it will stop the process. Is the amplitude dispersion the only method and parameter selecting PSI? Yes, in the current implementation of the PSI, the persistent scatterers are based on the amplitude dispersion only. There is no like other technique you can select.
So Gabriel, actually, I'd like, if possible, so one of the questions, just want to also get to this one. So is there a PSI workflow ready to run for an unexperienced user? Obviously, we showcase the very detailed modular workflow. But I think, and I just, so one of the things you were mentioning is that we also provide these scripts and helper scripts, which are more end-to-end, more black box concepts where you can provide just a simple set of parameters, point to your stack of images, and then you'd be provided with a displacement results or layers at the end. Is that, just want to verify, is that correct?
Yeah, there is a series of script that will be available online that guides you through this workflow, and basically you, of course, a basic understanding of the different operation always help to interpret the results. But basically, by running 3 scripts, and this is like plug and play, you can get to the result pretty quickly. So everything is pretty well streamlined and automatized using like
Wonderful.
scripts.
And I also just want to highlight as well that we also have our Insights platform, which is a web-based application where you can just access, if you just want the measurements themselves over a particular area, you can access the measurements through this application, and it's also being released on a variety of other platforms and marketplaces such as Esri's marketplace. So we give you a variety of ways in which you can, various levels of expertise or users of various levels of expertise can access these measurements, whether it's for research purpose where you want to play with every single parameter, or if it's you just want to generate the results on the desktop with our plug and play scripts, or if you just want to access just the measurements and we compute the measurements for you using our web-based application, which is Insights, all of these become available to you. Okay, I'm just going to identify, so we're running out of time here, so I'm just going to identify 2 more questions. And then, as I said, there's a lot of questions here, which is great. We really participate or we really appreciate this level of engagement. So one of the questions, actually, Gabriel, why don't I give you an opportunity to choose one last question, and then I'll choose one more after this.
Is the hybrid method used here similar to that one that exists at STEMS? I'll say yeah, it's a bit like STEMS in which you can like compute your persistent scatterers interferometry. You can using a baseline SBAS approach. It's not entirely like STEMS because we have a proprietary like tools, but yeah, it's similar. And one of the other question I've received, and all those questions will be also answered. If you don't have the time to cover this, we will answer it also later and you will receive the answers. But one other one is, if I go through the list, are we going to be able to export the individual pixel values extracted to a CSV or a text file? Yes. So at the end, what you get is a stack of data, or a stack of persistent scatterers, and then there is another script that we didn't cover here, but that extract the location of the points, their geographic coordinates, and then the measurements. So after that, with this, you can do the analysis you want with this file. Or you can visualize your persistent scatterers as well.
Wonderful. So, no, I really appreciate that, Gabriel. And so I'm going to just answer two questions that are a little bit more on the, I guess, about the product and the commercial side. So one of them is when and where will we be able to access the tutorials and the scripts? So we will post them on our website, and we will distribute and let you know where you can access them. But generally, you can go to our website and go to the Knowledge Center, and you'll be able to access all of our scripts then. We expect, and our tutorials, and we expect them to be available within the next couple days or the next few days. So we're working hard to get these tutorials up and online. The other question was about pricing estimation for a license commercially. So all of our prices are available on our website for Catalyst Professional. So you can go, I provided a link in the chat. So you can go to that link and you can review the different pricing options and subscription options. And of course, you can contact our sales team if you're looking for things like perpetual licenses as well. And we can help showcase or work with you to find the right solution. So once again, with that, I'm going to close things off here. We really appreciate your participation and attendance here. This is definitely a more technical